we are going to see the last topic of this unit, that is electromagnetic induction.
Mm.
And because of that, we do have so many applications. Like this particular concept, which we got in physics, has so many practical applications out there. So we're going to answer so many questions that we see around us. First of all, this image which you can see here. So how those dams actually able to create or generate electricity? We're going to answer that. Similarly, we are going to talk about that how these inductions work, how they're able to convert electricity into heat, to be precise.
Mm-hmm.
Then we'll be talking about these instrument. So any idea what it is?
Mm, some sort of meter,
Yeah,
like
it's some sort of meter, right?
and then it has like the poles, so like some magnetic. I
Yeah,
don't
it
know.
has two magnets, to be precise. There are two magnets there.
Mm,
And also there is a coil.
mm,
This positive and negative terminals represent that this must be connected to some sort of source. That source is something, sometimes can be a battery, sometimes it can be a generator or whatever you can think of it. So this
mm-hmm.
is something we called generator. So how that generator is actually able to generate electricity using some mechanical source, or you can say some sort of energy source that it might use. Sometimes it's petrol, or you can say gasoline, or sometimes diesel as well. So depending upon which type of generator it is, it uses some sort of you can say energy source, which can
Mm-hmm.
be petrol or diesel or gasoline. So in today's class, we're going to talk about these following things. First of all, we'll start with magnetic flux. Just like electric flux we saw in electrostatics, there is another term which we call magnetic flux. So first of all, we are going to define that magnetic flux. Then we'll be talking about what are the laws, those which Faraday gave in order to understand that how electricity is being generated using magnetic field. Then we'll talk about Lenz law. Lenz law is something which will give us the direction of induced EMF. Like whatever EMF or energy we are going to generate or electricity we are going to have, what is the direction of that? That in which direction or in which sense it is actually generated. Then we'll talk about motional EMF, again a different thing. When we reach to this topic, you'll get to know more about it. Then rotational EMF. Then we'll talk about eddy currents. So eddy currents is one such applications of, you can say, magnetic flux, because of which we do see so many negative aspects as well as some positive aspects also there. One such application of eddy current is electromagnetic braking. So whatever braking system do we observe in railways, sometimes in metros, or sometimes in whatever high speed moving vehicle, high speed moving trains, basically, they use eddy current. So we'll talk
Mm-hmm.
about that also. In one particular application, it's not only like that one application or one particular concept works. There are more than one or two concepts that combiningly work on it to make it possible. So eddy currents is one such thing. Then we'll talk about induced electric field, and that induced electric field is something which is because of magnetic field only. So how
Mm-hmm.
magnetic field is capable of inducing electric field, we're gonna talk about that also. So this whole thing comes under electromagnetism. As of now, we are aware of electric field, we are aware of magnetic field. Now we are going to see that how electric field is going to produce magnetic field, as well as how magnetic field is going to produce electric field, and what happens if any one such thing is there. So we'll talk about each and everything here. So first of all, let us try to understand what magnetic flux is. So by any chance, do you remember what is electric flux?
Mm-hmm.
what you saw in electric flux, like what it is.
Um, when like the
Electric
charge
flux,
passes through.
um, electric flux is something we can say when electric field lines passes through per unit area. Like how many number of field lines are actually passing through a unit area.
Mm.
That is something we call electric flux. And for
Those are
that,
these ones also like the red arrows here in the
yeah,
flux.
but
Oh.
here it is different. It is magnetic field. But in order to understand magnetic flux, first we need to have that understanding of electric flux.
Mm.
Again, electric flux is something which is electric field lines passes through per unit area.
Mm.
So if we try to write its mathematical form, we can say phi is the symbol which we use to represent electric flux, phi E to be precise. It is something E dot ds, that electric field lines passing through unit area.
Mm.
Similarly, here also, when we are going to define magnetic flux, it is nothing but magnetic field lines passing through per unit area. So these are the quite similar terms, or you can say these are completely analogy to each other. They completely have analogy to each other, and how they're going to work, what exactly happens when the flux changes, and how this electromagnetic induction thing works. We'll talk about everything here. So magnetic flux is something when through a closed loop. Whenever we are talking about a loop, it means a circuit which is closed. So you can
Mm.
say this must be a circuit, or this must be a wire, and it is closed. So whenever some current passes through it, so this current, whenever it is passing through it, it might cause some change in magnetic flux. So we'll talk about that. How does it cause that change? So magnetic flux is something when magnetic flux passing through a loop changes with time, or magnetic field lines force are cut by conducting wire, then an EMF is produced in the loop or in that wire, and this EMF is called induced EMF. If the circuit is closed, then the current will be called induced current.
Mm.
So in order to understand this definition to a greater extent, first of all, let us understand what is magnetic flux. So always remember, magnetic flux is something number of magnetic field lines pass passes through unit area. So as you can see in the diagram, this is something we can say area. That area must be, you can say, closed one. It should not be variable. It should be closed one. It should be finite. And when some field lines passes through that area, that too in a perpendicular direction. So that area vector, that is represented by n cap, and the field vector, which is represented by b vector. So
Mm.
if they both are in the same direction, so we must say that there must be some magnetic flux. And that magnetic flux is something which is given by B dot ds, closed loop integration of B dot ds. See, you might see that the terms, you might see that the symbols which I'm using to define a particular term is different when you're going to learn the same thing in the school, but the meaning remains same. It won't change. Symbol might be different, which your class teacher might use, but all the concepts will remain same. Completely, they will remain same. So, in order to understand it better, we would say that flux is something which is B S cos theta. So cos theta is angle between the field and the area vector. So in the first case, you can see that the field is also in this way and area vector is also in this way. So can you tell me what should be the angle between the field and the area, magnetic field and the area in this case?
Mm. But how would we know that?
Just try to see it. Field is this way and area is also perpendicular to it. So both the lines which you are observing here, they must be parallel. And if
Yeah,
they are parallel, what should be the angle between them? What should be the angle between these lines?
180.
If they are parallel, the angle between them is 0 degree.
Oh.
But if they are anti-parallel, like this,
Oh, then yeah. Mm,
then theta should be 180 degree. That is the angle between them should be 180 degree. So what is the value of cos 0 and cos 180?
um, I don't remember it off the top of my head.
So the value of cos theta is nothing but 1. Remember
Mm,
this. Cos theta, if it is cos 0, it is equals to 1. So whenever magnetic flux and the area vector are parallel to each other, we will observe that there is maximum flux. That's why it's written max flux. Whereas if area vector and magnetic field are perpendicular to each other, that is theta becomes 90 degree. And we know that cos 90 is nothing but 0. So
so
ultimately we'll see
cos
0 flux.
oh,
And in any other case where there must be some angle between the area and field line, so we'll say that the flux is nothing but dA cos theta. So we have
mm,
to use that value of theta, whichever it is. So it is the angle between area and, we can say, field.
mm,
So this is how we are supposed to understand it. Again, remember, if there is a area and some field line passes through that area, so magnetic flux is something that how many electromagnetic field line are passing through that area normally. Normally means area should be perpendicular to the area vector should be perpendicular to this area of the whichever surface we are using or surface we are finding out. So this is all about magnetic flux. Again, you can see that there is a complete analogy between electric flux as well as the magnetic flux. Electric flux is E dot dA, or you can say electric flux is E dot A, whereas
mm,
magnetic flux is something B dot A. So they both are completely same and the definitions are also same, but in place of electric field, we use magnetic field in case of magnetic flux.
mhm,
So let us try to find out what is the magnetic flux here through this area pi a square of a small circle, and it is given that the A is very smaller than capital R. What does it mean? Let us try to understand this figure. So basically here we have two circles, and in these two circles, the outer circles carries some current I, whereas the inner circle has no current. The radius of inner circle is small a and the radius of outer circle is capital R. The question says, what should be the magnetic flux? We have to find this. So as we know, magnetic flux is something which is B A cos theta. So this theta is what? This theta is the angle between the field, magnetic field, and the area vector. If
mm,
you look at the inner circle like this, so its area vector is something which is drawn perpendicular to it,
mhm,
perpendicular to the surface. Whereas the outer circle has some current I flowing through it.
mhm,
So if we try to find out the direction of magnetic field due to this outer circles carrying current loop, so we can say we will use right hand thumb rule, which we saw in the last class only, to
yeah,
find the direction of field due to current carrying loop. We use right hand thumb rule. So what does that rule says? It simply says that it says just curl your fingers of the right hand in the direction of current,
mhm,
and the thumb will give us the direction of field.
mhm,
So if you try to use it, if you try to use your right hand and put it in the direction of current, so we'll say that field is something which should be perpendicular to it like this into the downward direction. So
mhm,
current is in upward direction, area vector is in upward direction, magnetic field is in downward direction, and the angle between them should be 180 degree.
mhm,
So can I say that phi b is something which is B A cos 180?
yeah,
So, what is the magnetic field due to the current carrying loop? Let us try to find it out as well. So, if you remember in the last class, that magnetic field due to this current carrying loop is something like this is a loop, and you have to find the magnetic field at this particular point P, which is
Mm,
at a distance, which is because of this radius R. So, it is nothing but mu naught I by 2 pi R. This is the magnetic field value. This is something which we saw in the last class. What we can do here is we can simply substitute the value of magnetic field as mu naught I by 2 pi capital R, that is the radius of this bigger circle, into the area of smaller circle. Because we have to find the flux for which circle? This smaller circle. So we'll use the area of this circle only, which is pi a square times cos 180, and value of cos 180 is -1.
yeah.
So when we solve this, we get that flux is nothing but which is mu naught times I a square by 2R, that too of negative. So this is the flux through this smaller circle, and this is how we are supposed to find it. So just understand this thing first, that whenever we are going ahead, like covering the next unit or any other topic, so that topic must be linked to whatever we have done in the previous classes, and we need to have that information, that what we have already done, because you
Mm,
can't go ahead without having the knowledge, or you can say without revising what we have done before, because we are
mm,
going to use it again and again. Remember the formula of magnetic flux, and also remember the formula of electric flux. We might use it again and again.
mm,
All right. So let us try to understand what is electromagnetic induction. So in order to understand what is electromagnetic induction, let us see some experiment. So again, the discovery of electromagnetic induction was completely accidental. Someone did something, he observed a change, asked himself that why this change is happening, why there is a change, and the curiosity of that person discovered this whole electromagnetic induction thing. Let us try to understand what exactly happened there. So, in order to understand it, let us see some experiments. Like, for example, suppose this is a coil. Let me try to draw a coil. This coil is something which is connected to a galvanometer. So, as this is a coil, but there is no battery, right? So,
mm.
if there is no battery in the coil, is there any current?
No.
There won't be any current, right? But what happens is that accidentally someone figure it out that whenever a magnet is starting moving towards this coil, the galvanometer shows some deflection. It means if the galvanometer is showing some deflection, it means there is some current. There is some current in the coil. Understand it. When a magnet moves towards the coil, galvanometer shows deflection, which is evident to this fact that there must be some current in this loop. So again, we have no proper reason, we have no proper, we can say, explanation that why this is happening. So in order to understand it, that person tries to do several other experiments also. Let us try to see that what those other experiments were. Again, He took a coil, and that coil is connected to a galvanometer. Now, what this person did is he has the same magnet, but he made that magnet move in the opposite direction.
Mm.
Again, he observed that due to the motion of this magnet, whether it is going away from it, there is a deflection in the needle. But that deflection is now in the opposite direction, like this. So, again, we don't have any proper evidence, but we can say that when the magnet moves away from it as well, galvanometer again shows some deflection.
Mm.
That too in the opposite direction. So just think of it from the person's perspective who is observing this. Like you're looking at something for the very first time and you observe that because of the motion of the magnet only, there is a current in the loop. So this thing is like very new, completely, you can say, difficult to digest as why is it happening. But still, they keep on going other experiments too. So this was case one where the magnet was moving towards it. This is case two. Magnet was moving away from it. Next, what he tried is he just kept a magnet there and there was no motion of the magnet. So if there was no motion of the magnet, he saw that there was no deflection. So you can say if magnet was not moving, no such deflection was there. So one thing he came a little sure about is that the motion of the magnet is something which is responsible for the induction of current, or this is responsible for induced current. So whatever current which is induced here in this coil, that is something we call induced current. So he came to one such conclusion that, or you can say, by doing these first two cases, understanding these two cases, he just came to a conclusion that there must be some induced current due to the motion of the magnet. But this was not the case. So he moved a little ahead and did something else. Let us try to see what he did. Again, he uses a magnet and a coil. This is third case. He did the same. He uses a magnet and a coil. So now I can assume this is my magnet. And this magnet is at rest. And again, we had a coil, and that coil is something which is connected to a galvanometer. Once again. Now what he does is he keep this coil in motion. What he did is he started moving the coil, keeping the magnet fixed. Because of that motion, again he observed the galvanometer shows deflection. That
Mm.
is, still there is current. So just think of it from the person's perspective once again, that how this whole thing is there. And again, for the person looking at it for the very first time, it is very difficult to digest it. That because of the motion only, there is a current. Like just imagine you're moving something and you're getting current. How fascinating it is, right? Similarly, in order to make it more understanding, what he did is he moved coil in the opposite direction. And when he moved the coil in the opposite direction, again he saw the same thing, that there is a current. There is some induced current. So out of these three, four cases, you can say, or out of these initial three, four cases, the person came to the conclusion and he said that the relative motion between the coil and the magnet is responsible for induced current. But again, that is not the case. So, let me tell you the name of that person who was doing all these things. His name was Michael Faraday,
Mm-hmm.
one of the famous scientists of his era. He discovered several things during that time. Electromagnetic induction was his major discovery. And even today, we are using so many things which is based upon that electromagnetic induction concept only. So, in the fourth case, what he did is he somehow tried to make both magnet as well as this coil at rest. So, what he did is he keep a magnet this place and he keep a coil here also this way. In this coil, he attached a battery now this time, and through that battery, he connected a switch. Now things become a little change. So, what he saw here is that when he off the switch off the cell, or you can say when he turn off the switch, or when he even turn on the switch, because of that, what you can see here is that there is current, and this whole thing is connected to the galvanometer also in order to identify the current. Again, I told you about these two things, that there are two different components. One is emitter, other is galvanometer. Emitter is a traditional device which we use to measure the current, whereas galvanometer is a device which measures the small magnitude of current, like microamperes order. So it
Mm-hmm.
is capable of measuring a current of very small order. So that's why we are able to use galvanometer. We are using galvanometer here because whatever induced current we are finding in such cases, that the magnitude of such current is very small. So the traditional ammeter cannot measure it. So in order to see it, we are using galvanometer only.
Mm-hmm.
In the last case, what he did is that he just switched on this battery, and when he turned this battery or turned the switch on, we saw that there is a current in the circuit. So
Mm-hmm.
apart from this magnet, what he did is he again keep another coil around it. And now this coil is something which is connected to the galvanometer once again. Now this is the major finding. This is the major change that he observed, and this is something which leads to the discovery of this whole new law. So what he saw there is that when he turned on the switch in the second coil, let me call it as B coil and let me call it as A coil. So when he turned on switch, when he turned on the switch for that small time, There is a current in the coil A. What is going on? So what he did is he simply saw that when he turned on the switch of the coil B, so during that instant for which he's turning it on and turning it off, like how much time does it take to turn on or turn off a switch?
Like a second, less than a second.
Less than a second. You can say milliseconds. Like
Yeah.
it hardly takes a second, and we simply just turn it on and turn it off in milliseconds. So what
Mm,
he saw here is that when he is switching it off and switching it on, during that duration, which is very small, during that duration only the galvanometer shows deflection.
mm,
So because of this particular case, he got to know about this thing that whenever there is a current in a circuit, like whenever he was turning it on and turning it off, the current must have passed through it. So how the value of current must have changed when you just turned it on, when you just pushed on it. So current will slowly rise, and in a fraction of second it reaches to its maximum value of 5, right? But when this current is increasing slowly or it is going through the circuit, during that transition or the change in value of the current, for that period only there must be some magnetic field around it. And that magnetic field is something which is passing through this coil as well. So
mm,
this changing magnetic field for a very short period of time, again the time fraction is very small, this delta t is very small. The fraction of time which we are talking about, it is very small. For small to for that duration only. So for that duration only, what he saw is that the current will keep on rising for that milliseconds of time. And during that time, magnetic field, because of this coil, will also change. It will also keep on increasing. So these number of magnetic field line passing through this particular coil A will also change. Again, listen to the words carefully. The number of field lines which is being generated by coil A, it will pass through the coil. Again, number of electric magnetic field line passing or generated through this coil B will pass through that coil A, and during that change, like change, or you can say during that rise or fall of magnetic field lines passing through coil A, what does it going to do? It is going to change the magnetic flux of coil B, like number of magnetic field lines passing through coil A for during that small duration will get affected. Like number of field lines which is passing through it, it is started rising suddenly, and because of that only there is current. So if he is getting current due to this particular thing, so this thing must be valid in the earlier cases as well. Now let us try to figure it out that is it actually valid or not. So just try to see when the magnet is approaching towards the coil. So magnet must have some field lines. So when these field lines passing through the magnet and going through the coil, and that too it is going in such a way that it is keep on increasing. If the magnet is going towards it, the number of field lines passing through this coil will keep on increasing. Similarly, when it is going away from it, the number of magnetic field lines passing through the coil will keep on decreasing. What we have to understand here is number of field line passing through the coils keeps on changing, or I can say that number of or I can say that the magnetic flux passing through this coil is something which is changing. So ultimately, Faraday concluded changing magnetic flux is responsible for induced current. Are you getting it?
mm,
And this is the principle which we use in that electromagnetic, in that induction thing also. This is the principle which we use in the generation of electricity also. And in whatever device there is a something linked to the magnetic field, that principle somehow works.
Mm.
So now let us see what are the laws that Faraday gave for electromagnetic induction. Now you'll understand it more clearly. The magnitude of induced EMF, and in order to understand EMF, just remember it, the value current. Like we saw current in the examples only, so just assume it as a current. So magnitude of current is equal to the rate of change of flux.
Mm.
Like I said, changing flux is responsible for induced current. And to be precise, it should be changing flux is something which is responsible for induced EMF. So whenever the flux linked with the coil changes, it is ultimately responsible for the production of EMF, and there must be some induced EMF. So
Mm.
this is the case which actually works or actually happens in dams also. In dams, we are able to generate that electricity because of that whole thing when falls on the turbines and the turbines move, and because of the movement of turbines, the magnetic flux changes, and
Mm.
that changing magnetic flux is something which is responsible for production of EMF, and that
Mm.
EMF is something which can be further written as E is equals to IR. So we got the induced EMF, we ultimately got induced current. So this is how it is supposed to work. So this is what the law says. Understand it. The rate of change of flux with respect to time in case of loop is equals to the magnitude of induced EMF. Rate of change of flux means whenever there is a term called rate of change, it simply means you have to write this d by dt of that particular quantity. So this d
Mm.
by dt is something which is representing derivative. So in mathematical terms, we can say EMF is nothing but negative of d phi by dt. Now, what this negative sign indicates? This negative sign indicates that EMF will be induced in such a way that it will oppose the cause of its own production. Like why or however it is able to be there in that circuit, it will try to oppose the change in it. It will
Mm.
ultimately oppose the reason of its production, because this is how it is done. So let us understand it again by using this example. So whenever a magnet moving towards the coil go to the coil or just move towards the coil, the current in the coil will be induced in such a way so that it can oppose the motion of the magnet, so that it can oppose the movement of the magnet towards the coil. So if the
Mm.
north pole of the magnet is approaching towards the coil, the current will be induced in such a way that it will create a north pole in the loop so that it can repel it. Similarly, if it is going away from it, so it has to stop the cause of its own production. So it
Mm.
will induce current in the coil in such a way that it will oppose its motion. So how can it oppose its motion? By simply inducing current in the opposite direction so that this coil stops moving, or so that this magnet stops moving. So it will induce a south pole so that it can attract itself. So
Mm.
in every case, we have to understand it this way, that whenever there is a motion between the two coils, or you can say whenever there is a motion between the magnet and the coil, the current will be produced in such a way so that it can oppose the cause of its own production. This is what it says. And this negative sign is something which is given by Lenz law. This Lenz law gives us the direction of induced EMF, and that's why we are using this negative sign here.
Mm.
So electromagnetic induction is something we can say, but however we can induce EMF in the circuit. So by whatever way we can induce EMF in a circuit, that thing becomes electromagnetic induction. So electromagnetic induction is a creation of electromotive force by the way of moving magnetic field around the electric conductor, and conversely the creation of current by moving an electric conductor through a static magnetic field. So we
Mm-hmm.
try to move anything through a magnetic field, the magnetic flux linked with the coil, if we are able to change it, we will be able to induce EMF, or we will be able to produce EMF. So there are
Mm-hmm.
three ways by which we can actually induce current in the circuit. And let us try to understand what are these three ways. In order to see this, let us see what is the Faraday law says. It is nothing but d phi by dt. So d by dt of what is the value of phi? That is magnetic flux. It is nothing but Ba cos theta.
Mm-hmm.
So out of these three physical quantities, that is magnetic field, area, and theta, if we are able to produce change in any of these three quantity, we are able to produce EMF.
Mm-hmm.
So that's how we have three ways of producing EMF. First is moving a circuit into or out of the magnetic field, rotating the circuit within the magnetic field, and third, changing the intensity and the direction of magnetic field. So if we are able to change the direction or intensity of the magnetic field, we can produce EMF.
Mm-hmm.
If we are able to rotate the magnetic field, it means we are changing the angle, so we can produce magnetic field. And if we are moving the circuit into and out of the magnetic field, it means we are changing the area. So if we are changing the area, again we are able to produce the induced EMF. So in all the cases which we just saw in the earlier slides, like how dams are able to produce electricity, how that electric induction is able to produce heat out of the electricity, is all because of this. Because we are changing in these three things, like one magnetic field, other area, and the last a theta angle between the field and the area. If we are
Mm-hmm.
able to produce change in these three quantities, we are able to produce induced EMF. Remember the equation, E is nothing but negative of d phi by dt. This is how we are able to produce EMF. So let us do a small problem in it and we are able to understand it better way. Suppose there is a magnetic field which is given as 2 into 10 to the power minus 2 Tesla, acts at right angle to a coil of area 100 centimeters square with 50 turns. So let us see what we have given. We have given magnetic field as twice of 10 to the power minus 2 Tesla. We have given area as 100 centimeters square. Can you convert this 100 centimeters square into meter squares?
Um, be mm,
In our,
$1 centimeter.
I asked you to convert 100 centimeter squares into meter squares. It is going to be 10 to the power minus 2 meter squares.
Oh,
Yeah, you need to practice this conversion as well. Otherwise, because whenever we are solving question or a numerical here in physics, we need to use SI units. And the SI unit for that current, oh sorry, SI unit for that area is nothing but meter square, not centimeter square. So we have to make that change. So the
mm,
question is, the average EMF induced in the coil is 0.1 volt. So we have also given the EMF induced, that is 0.1 volt. Then it is removed from the field in t seconds. So we have to find the time, that is in what time this EMF is going to be induced. That is what we have to find. So let us see the equation of EMF. It is nothing but d phi by dt, negative
yeah.
of d phi by dt to be precise.
Mm,
So EMF is 0.1. What is this flux? Flux is something you can say PA,
yeah.
and for 50 turns we have to multiply this by n also. We have to see, we have given that the time is t seconds, so we simply write t over here. When we solve this equation, we'll get the value of time. Like T is going to be N is 50, magnetic field is twice of 10 to the power minus 2, area is nothing but 10 to the power minus 2 over 0.1. So if we solve this equation, we'll get 100 into 10 to the power minus 4 divided by 0.1. So this point 1 will go up and we'll get time is nothing but 0.1 second.
Mm.
So this is how we are supposed to solve this and this is how we are supposed to use this equation. Next we have is the total charge induced in the conducting loop where is moved in the magnetic field depends on. So here we have to answer that how this Q is going to change and on what factors it depends upon in the magnetic field. So again, let us see the EMF. EMF is nothing but d phi by dt, negative of d phi by dt.
Mm.
EMF is something that is potential and I can write IR in place of it from Ohm's law. I have simply used Ohm's law here. Now, what is this current? Current is nothing but dq by dt, rate of motion of charge, you can say.
Mm.
So in place of I can write dq by dt times R, it is going to be negative of d phi by dt. So this gt will cancel out this gt, so I can say this dq is nothing but negative of d phi by R. So now let us try to see the options and let's see how this total charge induced in the conducting loop changes when it is moved in a magnetic field. So rate of change of magnetic flux, it depends upon rate of change of magnetic flux. Initial magnetic flux only, total change in magnetic flux or final magnetic flux. So what is this d phi? This d phi is representing change in magnetic flux. So what do you think? Which should be the correct option?
Um, the A, the rate of change. Or
See the options again. I simply explained to you that whenever there is a term called rate of change means d by dt of phi. So d
mm,
by dt of phi will give us EMF, not charge. It won't give us charge. Understand it. Initial magnetic flux only. Initial magnetic flux means there is no change. We're talking about magnetic flux. So that is also not going to be the answer. Total change in the magnetic flux. And we can see here it. This dq is something which is directly proportional to d
mm,
phi. D phi is what? D phi is change in flux. But not we are not talking about rate. We're talking about the total change. Final
mm,
magnetic flux only. That is also not the case. That is also not possible. So C is going to be the correct answer. Charge is something which is directly proportional or it directly depends upon the total change in the magnetic flux. So this is how we can see it. Is it clear?
mm,
So we have another question. The question says phi is nothing but 5t square plus 3t plus 16. The question says what is the magnitude of induced EMF at t is equals to 4 seconds. So we
you just,
know EMF is nothing but d phi by dt. So
yeah.
if I able to differentiate this equation and substitute the value of time as 2, I'll get the EMF. What is the differentiation? What is the derivative of this equation?
10t plus 3,
If I substitute the value of t as 4, what I'm going to get?
43. So B 43.
Yeah, that is how you're supposed to solve this.
Mm,
Again, there are some questions and this is something you can do as a part of your homework. Now, Faraday law are consequences of conservation of energy. Remember this.
mm,
We are actually talking about energy only because if energy is conserved, then only we can see that something is going to convert into electricity. So the
mm,
here motion is something which is converted into electricity.
mm,
So if we talk about the dams, so we can see the motion of water is something which is converted into electricity. If we talk about induction, so in induction, there is the motor. So the motion of motor is something which is responsible for conversion of electricity into heat.
mm,
So again, Faraday laws is nothing but the consequence of conservation of energy. Whenever we are talking about law, it simply means that this is the fundamental phenomena that takes place. in this universe. It is not
Mhm.
something we can explain that why is it happening. It is something that it happens. That's why we are
Mhm.
studying it. It is a fundamental thing. So next thing is Lenz law. As I told you, Lenz law is something which explains us the direction of the induced current, that in which direction the current is going to induced. So you can assume this is a coil, and when this magnet is approaching towards the coil, so number of field line passing through the coil will keep on increasing.
Mhm.
Like if this magnet was initially here, and again if we see some field line coming out of it, so what do you think? How many field line will pass through this coil initially? Hardly any. But when it approaches the magnet, number of field line passing through the coil will keep on increasing. So the
Mhm.
number of field line passing through the coil keep on increasing. We can say that the flux is keep on changing. And
Mhm.
changing flux is something which is responsible for EMF. And to be precise, induced EMF.
Mhm.
So this is what it says. According to the law, EMF will be induced in such a way that it will oppose the cause which has produced it. So by whatever sense it is produced, it is simply says that it will oppose the cause of its own production. And this is
Mhm.
what uh, this law says, and this is how we're going to use it to find the direction of current.
Mhm.
So if you just look at the question, this question says the electron moves on a straight path xy. The ABCD is a coil adjacent to the path of the electron. So ABCD is the coil which is just placed parallel to the path of the electron. What will be the direction of current, if any, induced in the coil? So is there any current induced in the coil? Yes, there will be a current induced in the coil. How? Because we know if the electron is passing through this passing through the point X to the Y, there must be some current. And that current is something which must be there in this sense.
Mhm.
Current is something which is opposite to the direction of flow of electron. If the electrons are flowing from X to Y, the current must be flowing from Y to X.
Mhm.
So if the current is flowing from Y to X, we can say that the magnetic field, it should be this way, passing through the ABCD coil this way. So the magnetic field is passing through the coil this way, and this coil is something which is changing. This field is something which keeps on changing, and the as the electron is keep in motion. So as the magnetic field passing through the coil is keeps on changing, so it will induce EMF as flux through the coil changes. As flux through the coil changes. So we can say that there will be induced current, and it will be induced in such a way that it will be reverse the direction of electron when goes past through the coil.
Mhm.
Then we have motional EMF thing. So remember this phi is BA cos theta. So if we change the magnetic field, we can induce the EMF. If we change the area, we can induce the EMF. If we change the orientation, we can induce the EMF. So now we are going to understand that by how many ways we can actually induce EMF. First, by changing mass. Second, by changing area. And third, by changing orientation. So, the motion EMF is a case in which we actually change area to induce EMF. So what happens here is there is a movable arm of the loop, and this arm is something which is capable of moving in this direction. So the EMF
Mhm.
induced due to this flux change is something which is written like this. What is magnetic flux? Flux is nothing but dA. So if we write the area as this Lx, let's say it has moved x in the given time t. So the EMF
Mhm.
is going to be d phi by dt. Magnetic field is something which is constant. Length of the loop is something which is constant. So what left hand side is this distance x, because this is something which just keeps on changing as this arm moves.
Mhm.
So the differentiation of this arm or the derivative of this arm will give us the velocity of this arm. So the EMF is something BLT. This is something we call motional EMF. Why?
Mm-hmm.
Because this EMF is created due to the motion of the arm of the given coil.
Mm-hmm.
This is what it says. This is how it is represented here. In the generators also, motion EMF works. The motor, it is connected to this, you can say, coil. It keeps on rotating it.
Uh-huh.
And because of the rotation, the magnetic field passing through these magnets will keeps on, the magnetic field passing through the magnet will induce flux, will change flux of this coil. As in the different orientation, the flux will keeps on changing. And when there is a flux which keeps on changing, there must be some EMF. And that EMF is something which is being used by the appliances.
Mm-hmm.
The generators do use magnetic field to produce EMF, and generators do use motors to run through, you can say, diesel, gasoline, or petrol, whatever it is. So if you want to have a source of electricity, you can have a generator and some energy source. It can be
Mm-hmm.
any source which can rotate this motor.
Mm-hmm.
So here we simply have to use this relation to find out the EMF induced. And again, this is quite interesting, as whenever an airplane or a flight takes off and moves continuously over the surface of Earth for like a long time, like 10 hours, 20 hours, like that time. So during that time, it's the field, the Earth magnetic field is something which produces that EMF through the wings of the, you can say, flight. And then when that flight lands, the first thing the flight does is pass the all excess charge through the surface of Earth to make it completely safer for the passengers to came out of it. So when you see that when flight lands, it doesn't allow passengers to exit the flight like right away. It
Yeah.
take 5, 10 to 15 minutes to get everything settled down in terms of this charge, this excess charge which is being there on the surface of the flight.
Mm-hmm.
So you can simply calculate that what is the induced EMF across the ends of the wings by using the given relation and the given data. If the speed is 100 meter per second, the magnetic field is 5 times 10 to the power minus 3. Length of the span, wings is 10 and speed is 100. So it is coming out as 5 volts. So you can
Mm-hmm.
see that there is some potential that is automatically developed across the wings because of the motion of the flight through that Earth's magnetic field.
Mm-hmm.
Then there is this AC generator. Again, this AC generator use the same thing. You can even generate electricity by revolving it in the direction using your hand. If you do it like mechanically also, you can produce electricity. And you
Mm-hmm.
must have seen such models where a bicycle can produce electricity to run the
Mm-hmm.
light bulb. So that is something which is done by the AC generator only. This is something which uses electromagnetic induction as a principle to generate electricity. So this is one such very popular, you can say, model topic which students do prepare for the science exhibition thing, in which they used to produce electricity by simply converting mechanical energy into electricity by
Mm-hmm.
using AC generator. So the working of AC generator is based upon the principle of electromagnetic induction. That is something you need to understand. Then AC generator is something which converts mechanical energy into electrical energy. Again, a very basic thing about it, and you need to understand it. Now, the next thing we have is eddy current. So eddy currents are something which are generated on the surface of the conductor automatically due to the changing flux.
Mm-hmm.
So if there is a if there are magnets, and let us say that these magnets are not permanent magnets, these are temporary magnets, these are electromagnets. So when electricity passes through them, they generate a magnetic field. When electricity doesn't passes through them, they do not generate magnetic field. So because of these magnets, what happens is that the conductor actually get magnetized and demagnetized over a period of time. Like
Mm-hmm.
when we passes the current, it generates magnetic field, and the conductor which is being placed around it becomes magnetized. When you switched on the current, the magnet stop behave like a magnet because they are not permanent magnets. So the conductor becomes demagnetized. Because of the continuous change in magnetization and demagnetization of the conductor, there is a certain type of current which develops across the surface of the conductor, which is called eddy current. And this eddy current is something which is responsible for the high heat which is being generated across the surface of the conductor. Like you can understand it through this way, that if you look at the back side of the refrigerator, which is there at your home, it might be at a higher temperature.
Mm-hmm.
The temperature of the back side of the refrigerator is generally at a higher side. Similarly, there are a few other appliances also which which in which we do see the same thing. Similarly, in the television also, there are some magnets, there are some coils. When electricity passes through them, the whole surface becomes magnetized, and for some period of time it do show us some current. That's why the appliances doesn't that's why most of the appliances doesn't have metallic body, because of the if there is a metallic body, it's not like that they become more solid and they'll be like more durable. It's simply like that there will be more energy loss, and that energy loss is something which we can't bear easily, because energy loss is something which is there in the form of heat, and that loss is something which do increase our electricity bills. So we
Mm-hmm.
try to reduce it by simply replacing the metallic body by the some other non-conducting bodies, or by simply laminating the metallic
Mm-hmm.
conductor. So that's the case, and because of these eddy currents only, we do saw that in some of the conductors or in some of the appliances, there's a small amount of current that flows over the surface of the conductor, or it flows over the surface of the appliance. So that is what eddy current is. So let us read it and get to the conclusion. So eddy current is the induced in bulk pieces of conductor when it is placed in a changing magnetic field. So as I said, if there are permanent magnets, and if we turn on the current, they behave as a magnets, and they will produce magnetic field. When we turn it off, so the magnets stop behaving like a magnet, because they are not permanent magnets; they are temporary one. So because of that changing magnetic field, the conductor has some magnetic flux induced in it. And what it does is it will induce EMF on the surface. And this
Mm-hmm.
will derive current around the circuit. And the alternating magnetic flux induces eddy current in the iron core and causes heating. So that is the main flaw of eddy current. But we do use it as so many applications. Like in induction, we produces magnetic eddy current to such a large extent that this heat is being used to actually heat up. Similarly, we use the same thing in geysers as well as there are some heaters which we do use during winters. Those heaters also work some on the same principle, like same principle of eddy current. We are converting the electrical energy into heat energy. So we do use it to produce heat, but most of the time this is something which is disadvantageous to us. So we always try to reduce it because it causes a lot of energy loss.
Mm-hmm.
If we talk about the advantages of eddy current, so there are electric brakes which do use eddy currents. There are induction furnace which do use eddy current as a application. We have energy meters, we have speedometers. So these things are something which uses eddy current in a beneficial way, you can say. So eddy currents are produced when a metal is capped in a varying magnetic field, a metal is capped in a steady magnetic field, a circular coil is placed in a magnetic field, through a circular coil current is placed. So what do you think? What should be the correct answer?
Mm. When a circular coil is placed in the
This,
mag.
the shape doesn't matter. See, within the conductor will change its magnetic flux linkage and subsequently induced EMF. So when there is a magnetic flux changes, or you can say that the magnetic field passing through the conductor changes or the loop changes. So whenever there is a varying magnetic field and there is a metal that is kept in that varying magnetic field, so automatically eddy current will be induced in it. So A will
Mm.
be the correct answer. If metal is kept in a steady magnetic field, so there will be no flux, no
Mm.
magnetic flux. This implies no EMF.
Mm.
This implies no eddy current. Similarly, the shape doesn't decide whether the current is going to be induced or not, whether it is circular or anything else.
Yeah.
What's important is varying magnetic field. That the magnetic field should vary.
Mm.
That is something which is important. Next, in which of the following devices the eddy current effect is not used? Now, I guess you can answer.
Oh, the magnetic braking in the train.
See, so electric braking, induction furnace, energy meter, speedometer. Electric heaters, we do use eddy current.
Oh,
Electromagnets, we do use magnetic current. Induction furnace, we do use magnetic field or the eddy
yeah.
current. In magnetic braking, there is something else, and that is something which is called hysteresis. We'll talk about it in the upcoming classes. So yes,
So
magnetic
the
braking in train.
magnetic brake is different from the electric brake, right?
Yeah, which is completely different. Although
Okay.
it is linked with electromagnets also. Because
Oh,
these are linked with electromagnets. These are not completely alone. These are linked with electromagnets only.
mm-hmm.
Then the last topic of this particular unit, that is induced electric field. So when magnetic field changes with time in a region, then the electric field is induced within and outside the region. How can you say that? Just try to understand it. So if we are able to produce or if we are able to change magnetic flux, we are able to produce EMF. We are
Yeah.
able to produce current.
Mm.
If we are able to produce current, it means we have made charge in motion.
Yeah.
It means there are charges, so there must be some electric field. And the reverse thing also goes the same. And that is how we can say that the induced magnetic field can produce or induce electric field as well. So this is something which you have to just understand how this thing actually works. So just remember this thing. If there is a induced EMF, induced current, because of the changing magnetic flux, there will be induced electric field as well. So remember this whole sequence that how this is going to work. So if there is a magnetic field, it has a capability of producing electric field. And the vice versa is also applicable. If there is electric field, it can produce magnetic field.
Mm.
So we try to understand the properties of these things. The field is different from the conservative electrostatic field. I'm talking about magnetic field here.
Mm.
It is non-conservative force field. Now this word non-conservative is something. on which I can conduct a whole class. So I would say that it is something which doesn't depend upon the path. Like a different thing, we need to understand it like in more detail in order to have understanding properly. You can't understand it by simply learning this word. So we'll talk
Mm-hmm.
about it in coming classes. It's field line always in closed loop. So whenever there is a field line, they always form a closed loop like this.
Mm-hmm.
It should not be open, it should be closed loop. If F is equals to QE, it is an electrostatic force. It is valid for the field. Which field? Electric field only. For one complete loop, potential will not be equal to zero. So if we talk about a loop, so potential is not going to be zero for one complete loop. There must be some potential. Here it says electric flux, that is E dot dl. For new field, it is not going to be zero, but for old field, it is going to be zero. Now, what this new and old means? New field means something which is there because of the changing magnetic flux, and old field is something which is there because of the non-moving charge. Now, understand it this way: if there is magnetic flux change, if there is change in magnetic flux, it will ultimately induce current.
Mm-hmm.
It means we ultimately put charge in motion. So if charge is in motion, there must be some field, that is new field that will arise due to the motion of the charge. So
Mm-hmm.
this product is not going to be zero. But if there was no magnetic flux, so the charge, it will stay at rest. If it will stay at rest, we can say for the old field it is going to be zero. Similarly, the direction of induced electric field is same as that of induced current. So in whichever direction you will observe the current, in the same
Mm-hmm.
direction we will observe the electric field as well. So we can do this question also. Flux
Mm-hmm.
linked to following coil changes with respect to time, then for which coil EMF is not induced. For those coils which are not conductor in nature, obviously,
Yeah.
there will be no induced current or there will be no induced EMF if the coil is not conducting in nature. So you can
Mm-hmm.
say it's two coils. So that's all for the class. That's all for the unit.
Mm-hmm.
And again, there are a lot of things which you can discuss and in detail, like we can discuss vectors here, we can discuss